try somehow to get together with your collaborators. Well, this is one of the most favorite pictures that Lorenzo likes to draw, even though I'm not able to, I'm not going to talk about heterodimensional cycles, but I would like to just forget about the cycle, and I will talk about dynamical systems which mix hyperbolicity of different types, so which in particular have fixed points, should be in dimension at least 3. Well, I will talk about some even more simpler settings, dimension 3, so that there coexist fixed points which are hyperbolic of different type, meaning that they have different the dimension of stable and unstable dimensions varies. Well, and our main aim is, in the long run, eventually, possibly, to understand, using big names, to understand the thermodynamic formalism of general diffeomorphisms or partially hyperbolic diffeomorphisms. Well, I think there is still lots of work to do in this direction, but some things are done. So partially, we want to understand robustly transitive C1 diffeomorphisms, assume that they are non-hyperbolic, and let's say they are partially hyperbolic, and have saddles of different indices. And Christian already mentioned this work by Gorodetsky. Well, in fact, Gorodetsky and his co-workers, Ilyashenko, Kletzin, and Narsky, when they asked to what extent the dynamical system is hyperbolic, and then also Lorenzo sometimes coins this phrase. I'm not actually sure if he coined this phrase, asking to what extent ergodic theory can detect hyperbolic dynamics and also non-hyperbolic dynamics. Okay, so putting some more conditions, for example, assume that your partially hyperbolic system is of the type that the central direction is one-dimensional, and assume that it's integrable and tangent to closed curves. Well, this seems quite specific hypotheses, but these are conditions are open and inside a class of robustly transitive and non-hyperbolic diffeomorphisms. And there is, Christian already mentioned some of those works that they show that the strong foliations, the strong stable and the strong unstable foliations are minimal. And for that, they use in these works, they also heavily use tools like blender horseshoes. And so here are some references which indicate these results. And in particular, they show that there do exist non-hyperbolic measures, meaning measures which have zero Lyapunov exponent, and they can even be shown with positive entropy and full support. Christian mentioned some works here. I forgot the paper by Bonatti, Díaz, and Gorodetsky from 2010, where they have shown that those measures have large support. And in my talk, I would like to talk about this existence of non-hyperbolic measures, and in particular, talk about the construction of those non-hyperbolic measures. Okay. So, there are systems which are diffeomorphisms where hyperbolicity coexists and is also intermingled with non-hyperbolicity. And so in particular, there exist saddles, hyperbolic fixed points of different type of hyperbolicity, meaning the dimension of the stable and unstable directions can vary. And under those hypotheses, there exist rich homoclinic relations, meaning that these saddles, or here just fixed points, they are stable and unstable manifolds intersect, and hence there coexist many horseshoes of different type. So the transverse intersection of stable and unstable manifolds of periodic points create horseshoes, and so that coexist horseshoes of different type of hyperbolicity. And there do also exist, as I indicated the references, many non-hyperbolic ergodic measures. In particular, well, because I want to work in partially hyperbolic diffeomorphisms, so of course you have the strong stable bundle and the strong unstable bundle. This will automatically be related to Lyapunov exponents, which are negative and positive, but there's also a central bundle, which can give rise to non-hyperbolic measures, meaning zero Lyapunov exponent. And because I work in this partially hyperbolic setting, then the central bundle is a candidate for the isolated subbundle, and it defines a central Lyapunov exponent. And if this is one-dimensional, then the corresponding potential is just a continuous potential. And hence, to study non-hyperbolicity or the existence of non-hyperbolicity just amounts in studying the spectrum, means the average of this continuous potential. Okay, so because of the coexistence of saddles of contracting and expanding types, so the spectrum of central exponents has negative and positive values. But as there do exist also non-hyperbolic ergodic measures, it also contains zero as a possible exponent, and the zero is in the interior of the spectrum. Okay, so the main approach that we worked with Michal is to focus on this splitting of the ergodic, of the space of ergodic measures. So forget about the non-ergodic measures, just focus on the ergodic measures, which are invariant under your partially hyperbolic diffeomorphism. So there are some ergodic measures which are contracting type in the central direction. There's some ergodic measures which are expanding, and there are measures which are non-hyperbolic, meaning having a zero Lyapunov exponent. Okay, so in a sense, this is an ergodic point of view of studying the disjoint pieces of dynamics, which were mentioned in the talk by Sylvain Crevissier. So you can ask if you have your generic diffeomorphisms, say partial hyperbolic diffeomorphism, in what pieces of dynamics here, what pieces of the and on the space of ergodic measures the ergodic measures split, and what is their structure? Do they intersect? What's the intersection? How large can there be the intersection? Or meaning in this case, is the set of zero exponent ergodic measures approached from other ergodic measures, hyperbolic ergodic measures, and what is their properties? So they can be of positive entropy, but can they be of large entropy? And what's the possible maximal value of entropy? Okay, so these are all questions which we are partially will answer. And while I'm not going to talk about diffeomorphisms, I will talk about, I will use the translation, well, lots of languages to be considered. So let me talk to translate. I would like to use this translation of this setting and the partial hyperbolic diffeomorphisms into a simpler setting. Lorenzo also likes a lot to study very simple models, which only at the first point of view, the first view look very simple, but they are very, in many cases, very simple, but still rich, and of course represent what you really originally want to study. Okay. So my setting will be a setting of this talk, and the results I will present will be a setting of a skew product with finitely many circle fiber maps, which will be C1 diffeomorphisms. So I have a look at the skew product with a simple shift in the first coordinate and circle fiber diffeomorphisms in the fibers. Okay, and I will even go to a much simpler example. I will assume that these fiber maps are piecewise constant, so there are only n fiber maps which act in the second coordinate. Okay, and one of the motivating papers and very inspiring papers is this by Anton, Ilyashenko, Klepsin, and Nasky from 05, where they also in fact studied ergodic non-hyperbolic measures. Let me just point out that there are such skew products that I will present, putting some hypotheses, which I will mention in a second. And those skew products, they capture the key mechanism of the class of the partially hyperbolic diffeomorphisms that I presented in the beginning. And there is a certain dictionary which translates from the partially hyperbolic dynamics to the skew product and vice versa. In fact, well, this was described in the work of us from 2017. And partially we did already the translation in the work with Bruno Santiago, and there's still work to be done and going on. Okay, but last but not least, there is also important examples which are represented by these skew products. There are which are the co-cycles, matrix co-cycles. When you take 2x2 matrices and look at the projective action, which gives rise to these circle diffeomorphisms. And in particular, when you allow for elliptic matrices, then you are in study an important class, in fact, an open and dense subset of elliptic SL2R cocycles. Okay, so let me say something about the hypotheses we want to assume. So in the beginning, I would like, in the following, I would like to heavily use the following assumptions, hypotheses that we want to put on our step skew product. So again, we have a step skew product from the shift space and the circle fibers to itself. First coordinate is just a simple shift, and in the fibers, these C1 diffeomorphisms. And we assume the following properties to be satisfied. So in all the, well, in many works of Lorenzo, there is somewhere a blender going on. Here it's just a blending interval. So there's just on the circle, there is somewhere a blending interval J, non-trivial closed interval, and you assume the following properties to be satisfied. Well, first you assume that your system, you want to have somehow transitivity of your map. So assume that there exists some point which has a dense forward orbit. And here in this axiomatic approach, I want to describe, when I talk about the orbit, sometimes I will talk about the orbit by the induced iterated function system. So I take a point in the circle and I apply all the possible concatenations of circle fiber diffeomorphisms. This will be the orbit of an iterated function system. Okay, so this takes care of transitivity. The second property, which we call CEC for controlled expanding covering. I put here the plus because I will look at the diffeomorphism induced by the circle fiber maps going forward. There will be a corresponding concept going, just taking their inverse maps, and then I will put here a minus. Okay, but not for now. So the second condition is that there is this controlled expanding covering, meaning that whenever I start with an interval, it should be sufficiently small, an interval that intersects my blending interval J. Then there's some iteration by my iterated function system. So there's some sequence eta in the sequence space, such that when I concatenate these corresponding fiber maps, the L first fiber maps for some L, then the image of this initial interval covers my blending interval. Okay, and the property should not only cover, but there should be some expansion for some universal constant K, which does not depend on the interval and not on the sequence that I find. Okay, so you get some intrinsic expansion property associated to this blending interval. And finally, there's also an accessibility property also going forward relative to the iterated function system. And for all of these three properties, there are the corresponding backward properties by looking at these inverse maps. So accessibility requires that the orbit by the iterated function system of my blending interval covers the entire circle. And in fact, because we have a closed interval and the circle is compact, so there will be covered by finitely many images. Okay, so this is the axiomatic approach. Okay, so let me just mention one example, which already was the motivated paper for this line of research by Gorodetsky and co-workers. So if you have just two fiber maps, one which makes an irrational rotation, and another one which is a north-pole-south pole map, then you could choose a sufficiently small interval which contains this expanding fixed point. You can show that this type of system, these fiber maps give rise to a skew product which has satisfies these hypotheses. There's another class of examples which are induced by blender-like. There are so-called blender-like examples, but I'm not going to talk about them. Okay. So let me just, yes, and also this example, what you see in the slide is, well, it presents an important example of the projective action of SL2R matrices, where you have here just one rotation induced by a matrix which represents a rational rotation, and then just another matrix which is hyperbolic, and it has this induced projective action. Okay, so they're important examples. Let me just we want to understand the basic pieces of ergodic measures and their relation to non-hyperbolic measures. So this is a picture theorem of, well, rough form of first result that we showed. Is the hyperbolic approximation of non-hyperbolicity. So for every ergodic non-hyperbolic measure, let's say with positive entropy, every such measure is weak star and an entropy approximated by hyperbolic measures. And in particular, it's approximated by horseshoes of either type of hyperbolicity, such that, so you have a sequence of horseshoes, let's say gamma n plus of this type, such that their topological entropy converges to the entropy of the non-hyperbolic measure, and also their set of ergodic measures supported on this horseshoe converge to a weak star topology to the non-hyperbolic ergodic measure. Okay, and in particular, these horseshoes carry ergodic measures of hyperbolic type, which also there can be chosen ergodic measures of hyperbolic type which converge in entropy and in the weak star topology to this non-hyperbolic measure. Okay, and there's a version for each type of hyperbolicity. So this was done for steps Q products in the work with Lorenzo and Michal. There's also a version for C1 partially hyperbolic diffeomorphisms with Bruno. Yang and Sheng also worked on this, and while they're not just us looking in this, studying in this direction, I would like to mention here also the work by Alita CBE, Jiagang Zhang for C2 diffeomorphisms. Okay, so I'm not going to talk about porcupines here, but I'm talking about one construction which are skeletons, and which in particular I would like to give a sketch of the proof of this theorem, which uses skeletons. Okay, so a skeleton is just a bunch of separated orbit pieces, which are, well, epsilon separated, and which are pieces of orbits of generic points for our non-hyperbolic measure, whose cardinality grows like entropy, and whose finite time Lyapunov exponents is approximately the Lyapunov exponent of the ergodic measure, so I got equal to 0. So you have in your system a bunch of orbits, and here I draw the orbit of a point in this circle by the corresponding map in the iterated function system. So along this piece of trajectory, you see roughly exponent 0. But then you can take this orbit and prolong assuming your using your accessibility property from the iterated function system forward and backward to meet your blending interval, and then you can use the you do this with the neighborhood, and you can use the controlled expanding covering property to get some expansion, and as a result you start with a small interval, you cover, and in total you see some expansion. So you start with a generic orbit piece of your zero exponent measure, you perturb this slightly, prolonged it, and you get some expansion, and well, you get an expanding iterated function system which maps expandingly some intervals to bigger intervals, and this gives rise to a horseshoe which is in the central direction and expanding time. So this is the rough idea how to use skeletons to show this hyperbolic approximation of non-hyperbolicity. Okay, and well, you can use this, do this in a way that the horseshoe has roughly the entropy of the original map, and is also weak star approximating your ergodic measure. Okay. Okay, so given a non-hyperbolic measure, you can produce this is somehow inserted in the set of ergodic hyperbolic measures. And next question you can ask is, what is the amount of non-hyperbolicity you have in your system? So, for example, in terms of entropy. So, what is the type of the type that prevails? Is it the hyperbolicity that has, for example, larger entropy, or is it the non-hyperbolicity? Does it have positive entropy? Yes, this is already answered, but what's the maximal value of entropy that's in your system? And this leads to asking for restricted variational principles for entropy and topological entropy of level sets. So there are two types of questions you can ask. You can ask for the maximal entropy of measures which are non-hyperbolic. Let's say for alpha equals 0, you ask for this number. And then you can also take the orbit-wise approach. Look at those orbits in your system and ask for the level set of points which have 0 Lyapunov exponent. And you can ask what's the size. And here I would like to, well, size I would like to understand in terms of entropy. So there is a very general variation principle, which is, for example, it can be found in the paper by Bowen, 73, which says that, well, this restricted variation principle is never bigger than the topological entropy, and in particular, you can put here the level set of points with 0 exponent, and you get this first result, which says that cannot supersede this number. Okay, so but you can ask what is this value, and in fact this is still an open and an interesting question we're not yet able to answer. And instead of writing a complicated theorem, let me just make a picture of the result that we show. This is not visible. I don't know why this is not visible. The references are not visible. So this is Díaz Gelfert Rams from 19 and Díaz Gelfert Rams just submitted. Okay, so we show the following restricted variation principle for entropy for the entropy of Lyapunov exponents in the setting of a skew product satisfying having these hypotheses stated in the axiomatic approach, which says that, well, there is an interval of possible Lyapunov exponents which covers negative and positive values, 0 in its interior, and the supremum of the measures of the entropies of ergodic measures with given alpha exponent alpha is equal to the entropy of the corresponding level set, and this is true for all alpha, including the alpha equal 0. So this, to show the theorem in its full has lots of steps. In particular, in the first paper we couldn't talk about the 0 exponent, that this is true for, in particular, for the value alpha to 0, and this is done in the second paper. And here, if I have managed to have time, I would like to talk about the construction of ergodic measures with 0 Lyapunov exponent and positive entropy. But let me just indicate some ingredients to prove this, to show this theorem. Well, first, let me mention that the pictures are always misleading, and I'm sorry about this, but I try to avoid heavy formulas. Well, first, the picture assumes proximality, in particular to guarantee that there exist precisely 2 measures of maximal entropy, which are hyperbolic of either type. Okay. Second result is what are the ingredients to prove this theorem? So first, you show that as I already said, there are many in your system. There are many saddles of hyperbolic type that give rise to horseshoes of either type of hyperbolicity, and each horseshoe, by classical results by, for example, Fist and Sullivan or Fendliau and Perrier, they been shown that they do satisfy this restricted variational principle, only that for them there is they are hyperbolic, so they have a spectrum of Lyapunov exponents on some, let's say, positive interval. So for each horseshoe there's an interval, and corresponding the spectrum of their entropy of their Lyapunov exponents. And then you show that taking bigger and bigger horseshoes, using the fact that there are plenty of homoclinic relations, you prove that those these graphs eventually approach the graph and in fact provide the formula for your spectrum covering any point in your spectrum. And the same you do for the negative Lyapunov exponents. Okay, so this takes care, and this is relatively general, these types of ideas. This takes care of the spectrum which is away from 0. The harder part is to show that also first that those 2 curves which are defined for alpha negative and alpha positive, that they do approach a common value. Well, they do, you show this. And to show that this common value, in fact, is the entropy of the Lyapunov exponent and is the maximal entropy of measures which are ergodic and non-hyperbolic. And I would like to talk about this result. So about the construction of the ergodic measures which are non-hyperbolic and which have as large as possible entropy. Okay. So, well, in fact, you can write this this restricted variational principle. This is in fact there's some pressure involved. I didn't write the formula for the pressure. I just wrote here this formula that states that this function E of alpha is in fact the Legendre-Fenchel transform of corresponding variational pressures that take care of measures, ergodic measures with positive and negative Lyapunov exponents respectively. And well, you show that this is a concave function, hence continuous, but in general, for example, questions like if it's differentiable, we don't know. So there are many open questions. Some of you perhaps find them interesting. Well, I find them still challenging, but I'm not going to talk about all of this. So so we want to construct ergodic non-hyperbolic measures. Well, again, getting back to the motivating paper by the Russians, they do construct ergodic non-hyperbolic measures, and the construction is by periodic orbits. So you start with one periodic orbit, let's say of expanding time. Then you take you construct the next periodic orbit that starts circling, approximating your initial periodic orbit, and then does also some sojourn, making perhaps some support, constructing some ergodic measure which visits other parts of your phase space, and then you continue doing this procedure, constructing a next periodic orbit, etc., etc. It also does this, does something else, and you construct a sequence of periodic measures which have weakened Bika-Lyapunov exponent, perhaps visit lots of places in your phase space, and then you show that they show that the limit measure is first a measure which is non-hyperbolic and ergodic. Okay, well, this technique has been used by several people. Unfortunately, when you follow such a strategy, as it was shown by Dominik Kvetniak and Marta Wanska, you do not get positive entropy. So if you just do a construction by periodic orbits and do this approximation, you cannot get positive entropy. And we would like to have measures with large entropy, positive and as large as possible. Okay, so this is not so easy. So I would like to give an idea of the proof of the following theorem that there is a sequence of non-hyperbolic ergodic measures such that they converge to a measure which is ergodic and non-hyperbolic, and its entropy is as large as possible. So at most, well, close to the entropy of the zero level set, which is the upper bound for entropy. Okay. So, and I would like to give an idea of what's these measures which we use. And to show that this measure is ergodic, you have to use this King or criterion for ergodicity of limit measures that Gorodetsky and co. already used stated and used for a limit of periodic measures, while we use a version of that for our sequence of measures which are non-periodic. So as a very rough idea, instead of using these periodic orbit measures, we take a sequence of measures which are on horseshoes, which are of positive entropy. Okay, so this is, in fact, we pointed out that Benji Weiss already used a similar criterion in one of his works. Okay, so again, I have the setting is that we have here the spectrum, and we take a sequence. Okay, no, I want to talk about, I don't know what I want to talk about. I'm a bit confused. Okay, so in fact, our starting point is measure mu, which is ergodic and of contracting type. And as I tried to convince you, can be chosen with entropy arbitrarily close to the entropy of our level set. And what I'm going to construct is an ergodic measure with entropy very close, with entropy close to this initial measure mu. Okay, so let us start from ergodic measure with contracting type with negative Hyperbolicity exponent. And the first step is to study contracting iterated function systems induced by So we study contracting iterated function systems. Let me use this abbreviation, which are iterated function systems on my blending interval J, or some appropriated interval J. So if I take my iterated function system by these fiber maps, and then I can consider some concatenation of those fiber maps. And I would like to call such finite word, just denote this by W. And if I have a family of words, then I will say that such a family of words defines a contracting iterated function system if, well, if it maps this interval J into itself by each such fiber map, induced fiber map. And so this is the first condition. And then the second condition, if it does this in a contracting way. So if this contracting, this concatenation has derivative less than 1. Okay. So I need to be a bit more precise because I need to have some constants. So I make a more precise definition of my contracting iterated function system. So I say that the family of words defines a contracting iterated function system with some parameters. If this does this with some parameters, so some initial contraction, some initial constant k, with some contracting exponent alpha. And a third condition is that I get into these contractions have finite time Lyapunov exponents inside some interval alpha plus minus epsilon. And I would like also to keep track of those intermediate contractions so that I have up to some constant k from all intermediate. So I start from my initial interval J, and all these images are eventually contracting, shrink in size, but I also have information about this contraction rate on the intermediate steps. Okay, so suppose that we start with an ergodic measure of contracting type. And the first result is, well, such skeletons, here skeletons appear again, do exist. So meaning that there is a family of words which defines a contracting iterated function systems with certain quantifiers, and in fact such that this contraction rate is close to the exponent, and this should be central exponent of my measure mu. And the cardinality of those words is close to the entropy of this initial measure. Okay, and here is just a sketch of the proof. Again, you take your skeleton of large orbit pieces which are generic from your ergodic measure, which have contraction. So they contract an interval, and then by the axioms, by accessibility, you can put this in your blending interval, backward and forward. And you can also use this controlled expanding property going backwards. So this gives you some contraction along from the blending interval into the blending interval. And because you choose here very long stretches which represent your measure which is contracting in the fibers, this entire trajectory will be contracting and give rise to a contracting iterated function system. Okay, so such words exist, such family of words exist that define these contracting iterated function systems. They define this family of words. So sigma n star is just a set of finite words built from our initial indices that give that count the fiber maps. Okay, so let me start with this. So let me take one of those this alphabet, which comes, well, which defines my contracting iterated function system. So this is a collection of words. And well, I can take this. So each of these turns gives me one iteration by some word W. And now I can take this W, concatenate, say, W1, and then I can take the next word from this iterated function system and can concatenate the next word again with the first word, and so I can, well, produce many words which are given from this alphabet. And so I look at the space of concatenated words, forward and backward, be infinite concatenation of those words, and I look at the shift on this abstract word space. And this defines me contracting iterated function system on the blending interval. And to each be infinite word, I find in the usual construction of an attractor associated to contracting iterated function system, there exists a unique point associated to a one-sided infinite word. So this defines you a map from the word space to your phase space, associating to each word, be infinite word. Well, you project each be infinite word, which reappears here in the first coordinate as an element in your original sequence space, and in the second coordinate you get a point in S1. Okay, so this defines an attractor, which is so I have here my word space with the shift on this abstract word space, and this projects to an attractor, and on which my map acts. Well, it's not the original map F, because you need to look at it's a semi-conjugation. It's a conjugation, but only at the right times you return to your blending interval. So this return time depends on the symbols you have in your sequence. And to get an F invariant compact set, fiber contracting in the fiber line, you need to take also all these intermediate iterates and this defines what we call a multivariable time horseshoe. Okay, so this is a major issue, major difficulty in this construction, that those horseshoes, they are constructed over a blending interval. So you can take a blending interval, follow along some iterations by your fiber maps, and you eventually get back to this blending interval. Though if you take another word, the return time to this blending interval may vary. So you get an F invariant compact hyperbolic set contracting in the fiber direction, but it's not a simple horseshoe. In particular, if you look at its return to this blending interval, the returns vary from sequence to sequence. There's an upper and lower bound for the length of these returns, but they vary. So in general, it will be difficult to control entropy, and there are the control entropy. There is a problem with these multivariable time horseshoes, and here are the nice examples that Michal found for illustration. Is if you just some simple observations. If you have a dynamical system, continuous map on a metric space, and two subsets A and B, which have these properties. So if they behave as well, A and B are the images of contained in the image of A and B are also contained in the image of B, then you know that your system has at least entropy 2. If they do so for some, let's say, second iteration, then they have entropy, well, let's say at least log 2, so over 2. But if you have, for example, a property that A is contained in the second iterate of A, and in the first iterate of B, and B is contained in the first iterate of A, and in the second iterate of B, for example, so if you have variable time of return to your initial image, then, well, it's not so clear what in general the entropy can be. And for example, if you're very unlucky, you can get just entropy 0. So you need to be very careful when you study the entropy of those multi-variable time issues. Okay, so okay, so this leads us to we had to study for some part coding theory. So again, we have here our set of words, finite words in your original word space, and we concatenate these words to be infinite sequences, be infinite concatenation of these words. And this leads to the study of so-called coded systems. And coded systems are just a be infinite concatenation of from a set of words. Well, here it's a finite set of words. And then you need to take the shift invariant closure. Well, I would like to be a bit more precise. I would like to distinguish between the be infinite concatenation of words and their embedding into the original shift space. So it's a different issue to just talk about the be infinite concatenation of words and their result as a be infinite sequence in the original shift space. And I would like to make this distinction. So if I take this inserted set and just take the be infinite the shift invariant closure of this set, this is called a coded system. Okay, so such a set of words is disjoint if no element is a prefix of another one, and hence if I have a be infinite sequence forward, I can uniquely decipher what concatenation of words I had in the beginning. Though their backward deciphering is not so easy, and here's an example that this set of words is disjoint. So if I concatenate any forward concatenation, I can precisely decipher, but backward they can give rise to, the same sequence can give rise to two different decodings. Okay. However, there's only a finite number of decodings possible, and if the set is disjoint, and the maximal number of decodings is just the maximal word length of the alphabet, the word, the set of words. And one important observation is if I have a set of words which is disjoint, when I take their power, so when I just take the from the set of words W, I take just M copies, and then this gives me rise to again a disjoint family of words. Okay. Now so I have this set of words which come from a contracting iterative function system. And now I start playing with this. I take these words and look at their concatenation. So if I have one W1 to WM in W, then this will be an element in WM. And now I will take those concatenated words and add a tail. And this will give me a new family of words. So for each finite concatenation of words, I add a certain tail which depends on these words. Okay, so I start from one family of words and get a new family of words by adding those tails. And there's a theorem that shows that that states that if you start with the contracting iterated function system with quantifiers, with exponents given by, well, the finite time Lyapunov of exponents are alpha plus or minus epsilon, then if you choose these, if you repeat sufficiently often, then this defines a contracting iterated function system which drops the Lyapunov exponent by its half. So you start from one finite time Lyapunov exponent alpha plus minus epsilon, you get one which is the half of the spectrum, so alpha over 2 plus minus epsilon over 2. And moreover, you can do this in a way that the length of the tails is controlled. There is some universal constant involved, which is depending on this, the properties of the blending interval. So important again is you start from a spectrum alpha and plus minus epsilon, you go to a spectrum which is closer to 0. Okay, so let me give you an idea of the proof. So again, you start here from my contracting iterated function system, which gets you lots of words. Contracting iterated function system, which says that from your blending interval J, when you concatenate those words m times, then an initial interval, the blending interval, for example, will be shrink a lot. And you know that, well, it shrinks more or less like the Lyapunov exponent. So this is according to the length of the words involved times alpha, well, plus minus epsilon. Okay, so the size of this is of that size. Now, if you would like to continue using your controlled expanding covering property, then you could take this interval and make this big again to cover the initial blending interval. Okay, but then you would kill the contraction rate. You would end up with a finite time Lyapunov exponent close to 0. So you don't want to do this. You stop at some point. So you follow those iterates, but you do this up to some point where your size of the interval is more or less like, let's say, alpha over 2. Okay, so you get some interval of a certain size, and then, well, eventually you would like to end in your blending interval J, so then you use the accessibility property to make your, which this interval may be somewhere in your place, doesn't need to be here close to the blending interval, but then to end up in this blending interval by some finite iteration. So this is more or less the construction of the, when you start with one contracting iterated function system, you get a new contracting iterated function system, which is just a concatenation of those finite sequences. Okay. And it consists of concatenating words plus some tail. And this sojourn exactly is the tail. And you can control its size, and it depends on some universal constant times the exponent. Okay. So I'm running out of time, lots of things to discuss. But I would like to give you some idea what measures eventually we would like to look at. So you do this construction of you get a cascade of contracting iterated function systems. Okay, so starting from an initial one, the next one is a repeatance of the former one plus a tail, and then this in turn gives you a next one, contracting iterated function system. And each time you have exponents, finite time Lyapunov of exponents closer and closer to 0. Each one has, it gives rise to a horseshoe, a multivariable time horseshoe. So now where come the measures come up. So you have this this picture that you concatenate the words m times plus a tail, but it's difficult because each of the words has different length. But you still keep the idea of concatenation. But if you, but this gives rise of a subset of sequences in your initial sequence space. But because of the variable time, it's very difficult to keep track of these sequences. So our solution to that was to talk about an abstract alphabet for each word space that just gives an alpha and a letter to each word. Just forget about that the word comes from a sequence, just each word is a letter in some abstract alphabet AN. And the modeling of the length you put into a suspension space. So, and so you have your abstract alphabet. So you have your abstract here in the base. This should be the abstract alphabet. And horizontally, you should see the roof of your suspension space. So in the base, you do your shift in your abstract alphabet. And this abstract alphabet gives rise to the B infinite sequence in your abstract alphabet gives rise to a B infinite concatenation of your words, which induces your horseshoe, and the shift in your word space, which comes from the shift in your abstract alphabet space, gives rise to a return map on your multivariable time horseshoe. Okay, so there's a semi-conjugation going on, but because, well, it's a semi-conjugation, but because of this controlled decoding, this semi-conjugation is finite to 1, in particular preserves entropy. So you can, to look at the suspension space gives a convenient way to model the dynamics on these multivariable time horseshoes. Okay. Moreover, you have control of the tail length of the roof length, because the roof height is just the concatenation, the length of the concatenated words. And you know that the concatenated words are m times concatenation of from the previous sequence of words plus a tail, and you have control of the tail. And I'm running out of time. And I just want to say that, so you have here your abstract word space. You put there Bernoulli measure on your base, on your abstract sequence space, and this lifts by your semi-conjugation to a measure on your horseshoe. So this is the image of a suspended Bernoulli measure. So the entropy of this suspended Bernoulli measure, I don't have time. Do you have some more seconds to explain the
yeah.
I think this
go quickly.
This is very, so you have control of the entropy of those of the sequences in terms of the entropy of the initial measure and some universal constant. Let me just write some constant. Okay, but I think well, then you also need to show that these measures do converge and that the limit measure is ergodic. but this can be done and it's a bit more complicated. So let me stop here. Thank you.
Thank you. I have many questions, but I don't think we have time for many questions. Maybe one person wants to ask one question.
So may I have a quick question?
Yeah.
Katrin?
Sure.
So about your very beginning results, your previous results. So you assume proximality condition to obtain that picture of the graph of the spectrum.
Yes. Uh-huh.
So if you don't have proximality, can't you prove that you have a similar graph with some multiple maximums?
So if you don't have proximality, so in general, you just know that the two graphs are concave functions. And if you don't have proximality, they could meet like this, or they could meet like this. You don't know what's the actual figure.
Yeah, this is the question. So so in the first picture that you drawn, it seems that it is flat, kind of flat, isn't it?
Well, you know that
you
there
have
are two concave functions that meet in the middle. That's what you know.
Okay. No, because in the first picture it seems that you have more than two infinitely many measure of maximal entropy in particular, isn't it? Am I right?
I don't know. What I'm saying, what you can show is that the two concave curves that meet in a common point.
Okay, so just comparing with partial hyperbolic setting, that you can guarantee that you have finitely many ergodic maximal entropy measures. This is why I'm worried. So you know that, I don't know, in the IFS case, it should be similar. So, under some condition, you have finitely many ergodic measures. So if you have finitely many, it seems that you can't have this kind of graphs. So it is something intriguing me.
Yes. Okay. You may have this, that you have finitely many and a flat.
So if it is flat, you have plenty of measures with the same entropy, maximal entropy, no?
Yes, I mean, you can, a priori, you can have this, you cannot exclude this possibility. You have several measures of maximal entropy.
They are not all ergodic. They are just
yes,
linear combinations of those two ergodic measures at the end of the plateau.
Exactly.
Yes.
So in the same level, okay, you don't have ergodic decomposition. They are not ergodic, of course. They should. Thank you.
May I pose a question related to this question?
Yeah.
Because when Alice said that if the graph is flat, you may have uncountably many measures of maximal entropy. Does it mean implicitly that the maximum is attained in each level? Or do you know if the maximum is attained in each level?
What we know is that there exists a limit. I mean, we know that in when we have this proximality, then there exists exactly one maximal entropy measure of positive exponent and exactly one maximal entropy measure of negative exponent. But at all other points, we only know that there exists a sequence of ergodic measures converging to. In
the proximal case, yes, assuming proximality. Otherwise, you don't, and you don't know also for zero. In particular, you don't know for zero.
But that, for instance, you could have a flat graph and still having only two measures of maximal entropy. No?
Yes.
No, I think no, because this graph is actually coming as kind of convex hull of ergodic measures. Yes, so if you have plateau, it means that the endpoints of the plateau must be exactly given by the ergodic measures.
Okay.
Okay, so maybe we stop here.